So in this video, we'll be looking at the synthesis of an acetal from a carbonyl. So by reacting our carbonyl with alcohol under acidic conditions, we'll be able to create an acetal. So what you'll see here is if we start off with that carbonyl, let's see, start off that carbonyl, which we react, so let's say R1, R2, call this R3, we react this with an alcohol. Under acidic conditions, what are we going to get? We will get this structure right here. We have an O with our R3 and an OH. Now, this is not an acetal. This is actually a hemiacetal. So it's half an acetal. Now, if we want to actually produce an acetal, we're going to have to react the hemiacetal with another equivalent of alcohol. So we have to react with some more alcohol, right? Again, remember, in acidic conditions, in order to generate our actual acetal, which would look like, not like that. It will look like this. Now, these hemiacetals, right, they are actually not going to be able to isolate it, right? We can't have them standing on their own. So if we get to this hemiacetal step through reacting with just one equivalent of alcohol, we're going to have one of two things happen. Either, one, if we react with another equivalent, we're able to go forward and generate the actual acetal itself, or, because, see, this is a reversible reaction, we'll end up just going back to our starting carbonyl. So now, if we want to take a look at the mechanism, but before we do so, right, you may be wondering, why is it that we may be interested in creating acetals? What is this useful for? Why are we trying to do this? Well, one of many other potential reasons is going to be for a concept that we'll cover in another video, but it's called protecting groups, right? With the idea of protecting groups, there are going to be certain reactions where we have a functional group that may be more likely to react than another, right? Say we have a ring and we want to react here. We have this is again a just a general reaction. There's no actual chemistry here necessarily, or no specific functional groups that we're going to be talking about. But let's say we have a group here and we want, this is this place that we want to actually react, but this position is actually more likely to react. So what do we do? Well, if we add what we have to do is if we add a protecting group, right? We add a protecting group, right, on this group here, then we have no choice but to react in our position of interest. So we end up forming the reaction here, and then we remove the protecting group. So we get our initial thing back, and this position then has whatever it is we wanted to attach to it. Okay, I know this drawing was not very good. It isn't very clear. It was pretty spontaneous, but hopefully the idea makes a little sense. But if not, again, don't worry. We'll be going into a lot more detail on protecting groups in on a separate video of its own. But anyway, without wasting more time, let's look at the actual mechanism, both the forward and reverse reaction mechanisms for forming an acetal from a carbonyl. So for the forward reaction, you'll notice a lot of this is going to look similar to the actual mechanism that we saw for our hydration of carbonyls. So we're going to start off in the same way, where we're going to start with our carbonyl being protonated. So what does this protonation do? Well, it generates that oxocarbenium ion. If you can remember, that oxocarbenium ion is basically activated for addition, right? By protonating our carbonyl, we basically activate it for an addition reaction. So that's what we're doing here. So we protonate, we end up with our oxocarbenium. That looks like this. So we have this oxocarbenium, which we now react with our alcohol, right? We react this with our alcohol through an addition reaction. So what happens is this lone pair here is going to go attach, push these electrons, so we have an addition. We'll end up with this. Maybe we have an O, an R3, an H. This is going to have a plus charge, and we'll still have the OH here. So what we'll have to do now is we're going to have to deprotonate. We're going to have to deprotonate and get rid of this hydrogen. So how do we do that? Well, we can use another molecule of alcohol to do so, right? We can use the lone pairs on this oxygen to grab onto that hydrogen and push these electrons, giving us R1, R2, this O, R3, and we still have our hydroxyl. So now this here is that this is the hemiacetal step. Now, remember, normally these hemiacetals cannot be isolated. They're either going to go forward to the acetal if we react with another molecule of alcohol, or it's going to go backwards to our starting carbonyl compound. So let's move forward with this reaction. So now we have our hemiacetal produced, so we're going to have to now react this hemiacetal with an alkyl oxonium ion. So what is an alkyl oxonium ion? It has a rather complicated name, but what it really is it's just going to be our alcohol with an extra proton, right? So it has a protonated alcohol. You can see through this deprotonation event, we ended up generating an alcohol that has an extra proton. So that's called an alkyl oxonium ion, or just simply we can call it that protonated alcohol. So we can use that protonated alcohol to be a source of protons to actually protonate this hydroxyl group here. So let's say we have this R3O, and there are now two hydroxyls here, so there's a plus. And what we're going to then do is use the lone pairs on this oxygen to grab a proton, push off these electrons, which gives us something like this. And what we're going to have to do now is an elimination reaction. So we'll use a lone pair on this oxygen to form a double bond and kick off this water because it's a good leaving group. So now what we'll have, something again that looks like that oxocarbenium, right? We have an O with our R3 double bonded. There's an oxygen. There's a positive charge. So now remember, this is primed for an addition. So we can use another alcohol and go ahead with that addition reaction. So now the last thing we're going to have to do now is going to be a deprotonation, right? We have this 3, but we still have a hydrogen there. So we're going to have to deprotonate. How do we do that? Well, we can just use another alcohol molecule to grab onto this hydrogen, push off those electrons. Hopefully there's some room for this in the screen, but we will then be able to generate that acetal where we have our R1, R2, OR3, OR3. So it's a little crowded there on the bottom, but this here again now is our product. So this is the forward reaction for our for synthesis of an acetal from a carbonyl. You'll notice that a lot of this is going to be repetition of similar ideas, right? A lot of this is just a series of protonation and deprotonation events. So you'll notice that's going to be a common theme in a lot of these different carbonyl reactions. But anyway, now let's see how can we go from our acetal back to our carbonyl, right? We saw that this is a reversible reaction, so let's take a look then at that reverse mechanism. For the reverse mechanism, right, how do we remove our acetal, or how do we get rid of an acetal and go back to a carbonyl? Well, we'll have to react the acetal with some water and acid. And then this is going to allow us to regenerate that carbonyl, as well as, our two equivalents of alcohol there. So what's the mechanism look like for this? So we'll start with our acetal. Let's see. I'm going to try to draw it a bit higher, so that way we may have more room for later. So what we're going to want to do here, actually, just for the sake of clarity, let's draw this bond out a bit more explicitly. O, R3. So what we're going to do is we're going to use one of our acids here, our H3O+, to actually protonate this oxygen. So we'll grab this, push this there. giving us that R1, R2, O, R3, H, and there's a plus, O, R3. What we're then going to do is we'll use the lone pairs here to push this, kick this off. This is a good leaving group. So this protonation is really just turning this OR3 into a good leaving group. So now we have a good leaving group, so we can sort of push these electrons down to form a double bond, kicking off this, so we end up just kicking off one of our R3 OHs there. And so by doing so, we end up with this guy right here. Oops, sorry, it's glitching a bit. R1, R2, we have an oxygen, this R3, and a plus there, right? This is an oxocarbenium. So what we can do is react this with some water. If you want to draw that structure out, feel free to do so. Let's just do that. So we have water, so we can do an addition. This gives us R1, 2, O, H2 plus O, R3. So what are we going to do now? Well, now we're going to have to deprotonate one of these hydrogens here. We'll use a water molecule to do that. Grab this guy, push this down, giving us R1, R2, OH, and we still have this guy here. So now, this is the hemiacetal, right? If you remember from before, we're now at the hemiacetal. So now we just have to go from the hemiacetal down to the carbonyl. So we're halfway there. So now what do we do with the hemiacetal? Well, we're going to have to protonate this OR3, right? We're trying to turn it into a good leaving group. Hopefully you see a pattern emerging here, right? A lot of this is the same, which also makes the mechanism a bit easier. So if you just think about it as a series of steps in terms of logically what it is we're doing, why we're doing it. So now think for a second. Why is it that we're protonating this OR3? By protonating it, we're turning it into a good leaving group. So can you kind of predict what we'll do after that? Well, it's going to be very similar to what we just did. We're really repeating the process one more time. So by protonating this OR3, make it a good leaving group, we can use one of the lone pairs to push down, form a double bond, and kick off that leaving group. So let's just do that. So now we end up with this R1, R2, OH, an O, an H, and an R3. Plus, remember now this is a good leaving group, so like we said, we'll use one of these electrons to push and kick it off. So now what do we have? We have an R1, R2, O, H, plus. So now the very last thing we have to do is deprotonate. So we can use a water molecule to grab this proton, use the electrons to push it off here, giving us that starting material, our carbonyl. And you'll notice through this process we've also generated those two alcohols. So this is the reverse mechanism. It looks a bit messy here, but hopefully everything tracked, everything made sense. So again, if this video was helpful, please show your support by liking and subscribing. Leave any questions you may have in the comments, as well as suggestions for future videos, and I will see you in the next one.